Hey everybody, so we're still talking about limits at infinity, and last time we talked about polynomials, and so we're going to take some of what we did there and now start thinking about rational functions, right? So rational function is going to be the quotient of two polynomials, right? So I've written y as p of x over q of x, where these are each polynomial functions. So we're just going to do a couple of examples and use these to demonstrate a few rules we can make that make finding the limits of polynomials, rational functions much easier. So let's just go ahead and jump in. Let's look at our first example, and I'm gonna give these a category based on the degree relationship between the numerator and the denominator. So the degree of a polynomial, remember, is the exponent, the highest exponent, right? The exponent of the leading term. So the first category we're going to look at is when the degrees are equal. That means the degree of the polynomial in the numerator is equal to the degree of the polynomial in the denominator. So let's use this example. Let's take y is equal to 4x to the fifth minus 3x plus 1. And in the denominator, we'll have a negative 3x to the fifth plus 2. Right, so these are both degree 5 polynomials. So let's look at what happens as our function goes to infinity, as the inputs get larger and larger. So as x goes to infinity, we want to examine this limit, right? So the first thing to note is we can take the limit at the top and the limit at the bottom. That's one of our limit laws. But all we're going to get is that, right, whenever we talked about polynomials, we know that both of these polynomials, well, the numerator is going to positive infinity, the denominator is going to negative infinity. And we end up with infinity over negative infinity, which does not equal -1. We've talked about this. We can't perform math in the way we think. We can't perform math the way we do with numbers with infinity, since infinity is not a number. So that won't work. We have to do something else. A nice trick to have in our pockets is that we look at the denominator and look at the highest degree in the denominator. In this case, it's 5. And we multiply this whole expression by 1, written as 1 over x to that highest degree in the denominator. Right? So in this case, 1 over x to the fifth over 1 over x to the fifth. This is equal to 1, right? The only place this is not equal to 1 is when x is equal to 0, because this is not defined, but we don't care. We're out at the big numbers. We're far, far, far away from 0. All right, so let's see what happens. We distribute this 1 over x to the fifth to each term in the numerator. When we multiply it by 4x to the fifth, we're left with just 4. When we multiply it by 3x, we're left with negative 3 over x to the fourth. And then we have 1 over x to the fifth when we multiply it by 1. In the denominator, we get negative 3 plus 2 over x to the fifth. Okay. Now I'm going to go ahead and apply my limit laws and take the limit of the numerator and the denominator. But we notice something nice about this. This is where this trick comes in handy, right? We have now an expression. This is the same function, at least it is for large values of x, but we have it in a way that makes taking the limit very easy, right? So we can take the limit of each term individually, but in the numerator, this x to the fourth term in the denominator and this x to the fifth in the denominator, those terms just go to 0, right? We looked at, this was one of the rules we had developed, and we're left with just that 4. That 4 doesn't change anything just because x is getting bigger. And the same thing happens in the denominator. That 2 over x to the fifth disappears, right? As x gets large, that gets to be almost nothing. And we're left with the negative 3. And so the limit as x goes to infinity of 4x to the fifth minus 3x plus 1 over negative 3x to the fifth plus 2 is equal to negative 4/3. Okay, let's take a quick look at a graph. Here is that function graphed, right? It's got some pretty interesting stuff happening near 0, but once we get not even very far away, notice we've also got a vertical asymptote. That's the solution to the root of that denominator as a polynomial. Here is our asymptote. Make that a little thinner maybe and dotted. Okay, right? This dashed blue line is our asymptote. The function in this case does pass through it at some point. It looks like or close to 1, but out here it's just incredibly close to it, right? There's always going to be some space, right? Because that 4x to the 5th and negative 3x to the 5th, those two terms dominate this rational function, right? When we get really big, negative 3x plus 1 doesn't really do much. 2 doesn't really do much. And we have almost just 4x to the 5th over negative 3x to the 5th, which is negative 4/3, right? But those little bits that I say barely don't do anything, don't do nothing. And so we get this tiny little gap between this, right? If you look at the scale here, that's a very small amount of difference between those two, but it's still a difference, okay? So what we want to notice is what happened here. When we multiply, when the degrees are equal, and we multiply by 1 over the highest degree in the denominator, every other term in the numerator and the denominator ends up being something with a power of x in the denominator, because it has to be, because they're all smaller degrees. Okay, they're all smaller degrees. And so it ends up looking like just the ratio of their leading terms, right? And this turns out to always be the case. If the degree of P is equal to the degree of Q, where P of X is going to be some polynomial. So this is a way we can write them out abstractly, all the way down to A1 X plus A naught. And Q of X is going to be B sub n, X to the n. Remember, they have the same degree, so they have the same highest power. Then the limit as x goes to infinity of P of X over Q of X is just going to be the ratio of the coefficients of the two leading terms, right? This A sub n and B sub n, the coefficients of the leading terms, just like we had here. The 4 and the negative 3 turn out to be the only thing that matters, because all the other stuff becomes really small relative to x as we get really large. And so the ratio of those two leading terms is really what matters. But when we take the ratio, the x to the 5th cancels out, it's just those coefficients. And this works for positive and negative infinity, right? So I could put plus or minus here, right? We only ever do one of these. I'm just saying that regardless of which one you do, you'll get this result. And this is a nice rule. We don't have to go through all these steps to take these limits. We can just cite this rule, right? We know that if we're looking at two polynomials, same degree, we get to do this rule. Okay, let's, come on, there we go. Doesn't like to go sometimes. Let's now look at the condition or the situation, the rule, the case, couldn't come up with that word, where the degree of P, the numerator, is less than the degree of Q, right? So as an example, I'm going to do y is equal to 5x squared plus 2x minus 1. And in the denominator, we'll have x to the 4th plus 2. So we want to take the limit again as we go to infinity. We'll get 5x squared plus 2x minus 1. We're taking this limit. Again, if we try to do the limit in the top and the limit in the bottom, they're both going to infinity. They're both they're both polynomials with positive coefficients. They're both going off to infinity, but we can't say infinity over infinity is 1. That's just not generally true. We can find cases where limits that are infinite over infinite turn out to have a limit of 1. But when we get infinity over infinity, or 0 over 0, or infinity times 0, things like this, we call them indeterminate forms. We don't actually know what's happening. We have to try something else. In this case, we're going to do the same thing we did before. We're going to look at the denominator and multiply by 1 over the highest power of x in the denominator over itself. So we're multiplying by 1 because out at infinity or towards our big numbers, we don't have to worry about 0. And let's see what happens. We end up with the limit as x goes to infinity. So when we distribute this in the numerator, we get 5 over x squared plus 2 over x cubed minus 1 over x to the 4th. In the denominator, I get 1 plus 2 over x to the 4th, right? Well, now we do that same thing. We take the limit of the top and the limit of the bottom, but notice what happens in the top. Each of these are one of the first limits we looked at when we have powers of x in the denominator, where the powers are positive rational numbers. In this case, we have 2, 3, and 4. Those are all going to 0. So the limit in the numerator is 0, while the limit in the denominator is 1, and 0 over 1 is, of course, 0. Okay, so this limit is 0. So just to review, keep in mind, this is a good example of both of these cases. When we first took the limit, we got infinity over infinity, or in the first one, infinity over negative infinity. The first one ends up having a limit of 4 over negative 3, or negative 4/3. This one has a limit of 0, right? So that infinity over infinity can't really tell us what's going to happen. We already see 2 different results. Let's look at a graph of this one. Let's get myself back to a good viewing rectangle for a second. I wish there was maybe there is, and I haven't found it, a nice home button or something like that that just automatically brings you back to this. All right, so now the case where degree in the numerator is less. Here is our 5x squared plus 2x minus 1 over x to the 4th plus 2. Lots of interesting stuff happening in the middle. Some pretty neat little bumps and curves happening. But as we get out towards larger and larger x, the function disappears, right? By disappears, I mean gets vanishingly small, as small as I want, right? It's already pretty small. It's less than 1/10 here. If I went out further, I can get it to be even smaller, right? I go out here. Whoops, well, I've gotten pretty small that I can't even see it anymore. Another thing we might have noticed is that the same thing was happening in the other direction, right? Nothing we did depended on us putting in positive numbers. So this will actually go to 0 in both directions, okay? So out towards negative infinity, smaller, larger and larger x, but in the negative direction, are also making this thing vanish, right? I think this is pretty intuitively clear. X to the 4th is just bigger than x squared for large x, right? Even multiplying by 5, if you take 10 to the 4th, we get 10,000. 5 times 10 squared is 500, right? That x to the 4th is much, much bigger. That 5 stops mattering pretty quickly once we get out for just a little ways, right? The other stuff matters even less. The 2x and the -1 and the +2, those matter so little when we put in a number like 1,000,000 for x, right? Everything else just disappears. That x to the 4th is just way bigger than everything else. And so it all just, that's in our denominator. So it makes this function incredibly small. And so we say it approaches 0. The limit is 0, okay? This, again, can be put into a rule if y equals p of x over q of x for polynomials p and q with the degree of p less than the degree of q, then the limit as x goes to, and this is again one that we can do it in either direction, this limit is going to be 0. Okay. Now, notice in our case, the one we just looked at, we're approaching from above. We're going to be positive numbers bigger than 0, but it could approach from either way. In fact, if I just change this to a negative x to the 4th, we now see that we're approaching 0 from below as we go out to infinity, but we're still approaching 0, right? So that doesn't change anything about about that result, right? It obviously changes the shape of the graph and other things about it, but doesn't change that result. So this is another nice rule. We don't need to worry too much when taking limits of rational functions, right? We first started with a rule for when their degrees are the same. We now have a rule for when their degree, the numerator is less than the denominator. Let's take a look at what happens when the degree in the numerator is greater than the degree in the denominator. Okay. All right, so let's do as an example y equals x cubed minus x squared plus 3 over x minus 1. Okay, so we're going to play our same game. The limit as x goes to infinity of x cubed minus x squared plus 3 over x minus 1. So this is going to be equal to, we're going to take the highest power in the denominator, which in this case is just 1, and multiply it by this neat version of 1. Again, we don't have to worry about it since we're talking about large numbers. 0 doesn't come into play. So in the numerator, we end up with x squared minus x plus 3 over x. And the denominator, we get 1 minus 1 over x. All right, let's do this a little bit more carefully. So we can split the limit between the denominator and the numerator. And in the numerator, well, I'm going to do it this way. We can look at the limit as we get x squared minus x plus the limit as x goes to infinity, 3 over x. In the denominator, well, I'll just leave it. We can do this one. All right, let's go through the easy parts. In the denominator, nothing happens to 1 as x goes to infinity, and 1 over x goes to 0. So our denominator becomes 1. I'm not even going to write it anymore. In the numerator, I've got the limit as x goes to infinity of x squared minus x, and then 3 over x goes to 0. So this all just comes down to the limit as x goes to infinity of x squared minus x. I'm going to factor out an x. So we get this, and we're going to do the limit as x goes to infinity using our product rule for limits. Both of these limits are infinity, right? What happens to x as x goes to infinity? It goes to infinity. X minus 1 does the same thing, right? It's just one number behind. So we've got two incredibly large numbers that we're multiplying together. We get incredibly large numbers, and we get infinity. Okay, and so this limit is infinite. Okay, and this is going to be the case whenever we have some kind of infinity, whenever we have the degree in the numerator greater than the degree in the denominator, right? It might be positive, it might be negative, but we're always going to have an infinite limit. We can even say a little bit more than that. Notice what this came down to. We had x squared, the limit of x squared minus x, right? And this looks a lot like the quotient of these first two terms, okay? And that is going to be the case, right? That the quotient of those first two terms tells us a lot about what this thing looks like. So what I can say as a rule is that for polynomials p of x and q of x, where the degree of p is greater than the degree of q, and let's see, p of x is going to be equal to a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, on down to a sub 1, x plus a naught. Let's give symbols for q of x. Q of x is going to be is going to be, its coefficients are b's. And remember, k here is less than n because the degree of q is smaller. So b sub k minus 1, x to the k minus 1, down to b sub 1, x plus b naught. Then the limit as x goes to infinity, and this will also be one that's plus or minus infinity. So let's put that in, right? Again, we don't take those limits at once. Typically, what I'm really saying is there's two different things we're saying here. The limit as x goes to infinity, and also the limit as x goes to negative infinity of p of x over q of x is going to be the same as the limit as x goes to plus or minus infinity a sub n x to the n over b sub n x to the k, which we can simplify to be the limit as x goes to plus or minus infinity a sub n over b, that's b sub k, b sub k x to the n minus k. Now, notice what I'm not saying. When they were equal, let's go back up there. When the degree of these polynomials was equal, then the limit was equal to the quotient of their coefficients, the leading coefficients. I'm saying the limit of the rational function is equal to the limit of this power function, right? So in the example I have here, if I had this rule when I started this example, I could have jumped straight to the limit as x goes to infinity of x cubed minus x squared plus 3 over x minus 1 is equal to the limit as x goes to infinity. And I just take the quotient of the first two terms, x cubed over x, which is limit as x goes to infinity of x squared, which is infinite, right? This is not the limit, but it tells me what the limit is, because now we have a power function and we have those nice rules for power functions. All it comes down to is this: when you take the quotient of these two, is the power positive or negative? And then is the quotient of their coefficients positive or negative? And using that information, you go back to those rules about power functions. If the power is even and the coefficient's even, everything goes to positive infinity, right? If they're odd, they look like a cubic. Positive infinity on the right, negative infinity on the left, unless that coefficient is negative, and so on and so forth, okay? So it just gives us an easy thing to look at when we want to compute the limit. Let's take a look at this function. Let's see, so turn that one off. Whoops, too many things. All right, here's the function x cubed minus x squared plus 3x over x minus 1. It's got a kind of neat thing going on at x minus 1. It has an asymptote. We see in one side it's going to negative infinity, on the other side it's going to positive infinity. What also happens is as we get further and further and further and further away from from 0, all that other stuff besides the leading terms, x squared plus 3x, the minus 1, all of that stuff becomes much less important. And we have something that's basically x cubed over x. In other words, it's close to x squared. So notice these two functions are very different near 0. But if I look far away from 0, right, as we get further out, their graphs start to line up. They have the very similar shapes, except for right near 0. In this case, at x equals 1, we've got this asymptote, so that's doing something very different than our regular parabola. All these other things happen there, but once we get away from that, it starts to calm down. The other stuff doesn't matter so much, and we start to look kind of like the parabola, right? We can zoom in here and see how close together these two things are, right? As we scroll through here, we see all that. And so that's, sometimes this thing goes crazy, sorry. So this is a neat thing that happens when we have the degree in the numerator higher than the degree in the denominator. Let's look at another one, this example I've got here. Let's look at it algebraically first, and then look at the graphs. So that one was y is equal to 2x cubed plus x squared minus 2x minus 4 over x squared minus 1. So we can take the limit as x goes to infinity of this whole thing, cubed plus x squared minus 2x minus 4 over x squared minus 1. Now I can apply that rule I just looked at a second ago and just look at the coefficient of these leading, sorry, the quotient of these leading terms, 2x cubed over x squared. We get the limit as x goes to infinity of 2x, which is of course infinite, right? So that gives us a good example of using that rule. But I want to do one other thing. Our function, our original rational function looks a lot like 2x when we get really big. That's one way to interpret this, but it's actually not quite that. If you perform long division on this, which I'm not going to do right now, but you can do long division, and you get a remainder when you do this. They don't divide out evenly. This can be rewritten as 2x plus 1. That's the result of the long division. I forget the names of everything. But then you end up with a remainder, which is -3. So you can write this as -3 over x squared minus 1. This is the same function, okay? Just written a different way. You can go ahead and get common denominators if you want to put it back together and see that they're equal. You're just using the same way you do division with numbers. If you wanted to write, right, if you take 17 divided by 5, you get 3, 15, subtract your 2, that's your remainder. So you'd have 17 divided by 5 is equal to 3 plus the remainder divided by the thing you divided by, right? We're doing the same thing here, just with polynomials. Look at this. This is the line, this part of it is the line 2x plus 1. This thing right here, what happens to this thing as x gets really, really big? It becomes almost nothing, right? Put in 100, you get 3 over 9,999, right? It's really, really small. Put in 1,000,000, that thing's basically nothing. So the difference between 2x plus 1 and 2x plus 1 minus 3 over x squared minus 1 goes away, becomes really small when x gets really, really large. So let's look at a graph now of those two things. Here's our original function. Here's this one we just took the limit of, saw that as we went out to positive infinity, the limit was positive. Sorry, as x went to positive infinity, the limit was infinite. But here's a graph of 2x plus 1. And look what happens away from 0. This graph looks almost the same. The difference between them is that minus, what was it? -3 over x squared minus 1. That accounts for this space. And the further out we go, the smaller that difference gets. Okay, right? You go back to this. If we were taking this limit to negative infinity, right? The limit as x goes to negative infinity of 2x cubed plus x squared minus 2x minus 4 over x squared minus 1, we can still apply that rule. Negative infinity. This would be the limit of 2x, just like above. We get negative infinity. Right? That's where that line goes. And we see the same thing here, right? In both cases, our red function, our original function is a little below the line because we're subtracting that tiny little thing. but it gets so close to it. And so out away from 0, this simple line and this non-simple rational function become very similar things, right? If you wanted to compute the value of that rational function, right? If I wanted to know what's the value at x equals 1,000,000, I'm not about to do 2 times 1,000,000 cubed plus 1,000,000 squared minus 2,000,000 minus 4, and then divide that by 1,000,000 squared minus 1. But I can tell you it's really close to 2,000,001 because it's really close to that line, right? And you can do that in your head. Okay, so that is it for this one. We've got 3 rules now for all the different cases, whether the degree of the polynomials are equal or which one's larger than the other. Okay. All right, I think that is it for this one. Thanks, everybody. I will see you next time.